It's my pleasure to present to you Professor Tuncer Acar from Turkey, and today he will speak about weighted approximations by sampling type series. So please, Professor
Okay,
Acar, go
thank you so
ahead.
much, dear Professor Vladislav, for your introduction. And thank you for inviting me to International Biweekly Online Seminar on Analysis and Differential Equation and Mathematical Physics. Today, I would like to present my research group's recent results on weighted approximation by sampling type series. And my presentation will compose of the following session. The first one, I will talk about the weight approximation by generalized sampling series. In the second part of my presentation, I will talk about weight approximation by exponential sampling series. Actually, the uh, name of this section looks like similar, but it's totally different because in order to talk about the exponential sampling series, we will consider the tools of Mellin analysis. So it's different from the classical analysis. In the third part of my presentation, I will present some examples of kernels functions. I will explain what I mean with kernel, and I will terminate my presentation with references. Okay, the sampling type operators are very useful tool in order to provide an approximation version of classical Whittaker-Kotelnikov-Shannon sampling theorem. Actually, this theorem was proved in the beginning of 20th century and proved by Whittaker, Kotelnikov, and Shannon independently. But today, this theorem is known as Whittaker, Kotelnikov, Shannon. By the way, these three names are not mathematicians. They are actually engineers, and they were just trying to model a signal, and they are trying to find a way, a method in order to model a signal. So they found the classical sampling series, and they proved the sampling theorem. And this theorem has been widely studied since 1980s. Actually, the pioneer of the sampling type series is Paul Buzer from Aachen University, Germany, and of course his collaborators and research group. And this version, actually the generalized sampling series, mainly depends on generalized sampling series defined by inequality one. Of course, here this series is meaningful for the function f, which makes the series is convergent for every x in R. And here we have a function chi, and this chi is a function from R to R, and which denotes a continuous and discrete approximate identity which satisfies suitable assumption. Of course, you wonder what kind of suitable assumptions. Actually, these suitable assumptions change according to the space of corresponding functions. And here, W is a parameter. So we are considering a family or a net of the operators as an approximation process. Uh, the main advantage of the operators GWG is to reconstruct a given continuous signal f. I'm saying signal because I'm trying to use the literature notions because, as I said, Whittaker, Kotelnikov, and Shannons were engineers, so they were trying to model a signal. But here, signal will equal to a function from analysis point of view. So our aim in this process is to reconstruct a given continuous signal f by its sample values in the form f of k over w. for all k integers and positive w. And for our comprehensive studies, we refer the readers and the participants to the references. I will show these all references at the end of my presentation. Most of the references belongs to Paul Butzer and their research groups and collaborators. Okay, in the context of approximation theory, as you know, Bernstein polynomials are considered as a pioneer of the theory of linear positive operators. Actually, Bernstein polynomials were presented for the algebraic proof of a well-known Weierstrass approximation theorem. And after construction of Bernstein polynomials, many other polynomials such as Sazmirakian operators, Baskakov operators, Kodovsky polynomials were introduced. But the mentioned operators acts on non-negative semi-real axis, or Bernstein polynomials are defined on compact intervals of real numbers. Since the Weierstrass approximation theorem is given for functions belongs to Ci, here I is any compact interval, the studies on approximation of functions by such operators were restricted on compact intervals of R. Yes, Sazmirakian operators and Baskakov operators work on unbounded interval, but only the positive real axis. And when we have an approximation process, the second question after uniform and pointwise convergence, what is the rate of convergence? So in order to find or in order to determine the rate of convergence, mostly we need an appropriate modulus of continuity, as you know. But it's well known that the classical modulus of continuity does not work for functions defined on unbounded intervals. In order to use the classical modulus of continuity on unbounded intervals, we impose the uniform continuity of the target function. So uniform continuity is a very strong and restrictive condition. And a similar problem occurs in case of Bowman-Koriokin theorem. Actually, the Bowman-Koriokin theorem tells us a systematic method to determine whether a family of linear positive operators, let me say Ln from Ci to Ci, but here please note that I is still a compact interval, is an approximation process. So the Bowman-Koriokin theorem does not work on unbounded intervals. And this problem was solved by Professor Akif Gadzhiev from Azerbaijan. And if I remember correctly, his PhD is from Moscow University under the supervision of Ibrahim Ibragimov. If I am correct, I don't remember exactly. And Professor Gadzhiev in 1974 introduced weighted space of functions, and he proved the Koriokin type theorem for functions belonging to these Neve spaces, that is weighted space of functions. And for the recent studies on weighted approximation of linear operators, I will show at the end of your presentation, we refer the readers to the references 6 and 7. In this part, in the third part of my talk, we present approximation behaviors of generalized sampling operators. As I said, generalized sampling series has been studied for 80 years. But when we check the all studies, authors or researchers consider the continuous function on compact intervals, or they assume the compact support of kernel function. And there is no study for functions belonging to weighted space of functions. But the main purpose of the sampling type series is to extend the approximation to whole real numbers. So this is a really very big gap Okay, after some preliminaries and proof of well-definedness of the operators given in one, the generalized sampling series, between the weighted space of functions, we will provide an estimate of the rate of convergence by means of weighted modulo of continuity. So as a corollary of this estimate, we present a norm convergence of the generalized sampling series. And in order to present a rate of pointwise convergence and upper bound for this convergence in a unique theorem, that means at the same time, we obtain a quantitative Voronozki type theorem via weighted modulus of continuity for functions belonging to weighted space of functions. And one of the main advantages in considering functions belonging to a weighted space is that any function that is bounded with respect the corresponding norm of the space can be unbounded with respect to the usual supremum norm. So this allows us to enlarge the class of functions for which we consider the above approximation problems. Indeed, in literature, approximation results by means of the generalized sampling series have been mainly considered only in the space CR or in the other function space, but not of weighted type. So the results presented in this part of my presentation were obtained in a collaboration with Professor Osman Alagöz, Professor Ali Aral, Professor Gianluca Vinti, Professor Danilo Costarelli, and my PhD student Metin Turgay, recently published in the journal Demonstratio Mathematica. Okay, throughout the paper, a function chi is a function from R to R, will be called a kernel function if it satisfies the following assumption. The first one, chi1. Chi is a continuous function on whole R. And the second one, the discrete algebraic moment of order 0, that is the algebraic moment will be denoted with this notation, so which acutes to 1 for every u in R. And there exists a positive parameter beta such that the discrete absolute moments of order beta are finite. Yes, the following lemma holds. Actually, this lemma is proved in that paper and very useful lemma. Let chi be a function satisfying the previous condition chi1 and chi3 for every positive delta. There holds these limits. This convergence is satisfied uniformly with respect to x. And again, it follows from the paper 28, lemma 21i, that the gamma order absolute moment of chi is finite when gamma is a parameter between 0 and beta. That means if we know the finite case of the absolute moment of beta, that means the smaller degree absolute moments, are also finite. Of course, the function chi satisfies the assumption chi1 and chi3. And the function w tilde is called a weight function if it's positive continuous function on the whole real axis. This is our first condition. And in the study, we consider the weight function w tilde x 1 over 1 plus x squared. That is, we are considering the polynomial weight. Of course, you can ask me why you are considering a polynomial weight, because of the structure of the algebraic moment and absolute moment. Of course, you can consider any other weight function by constructing the following weighted spaces. The largest space is denoted by BW tilde. By BW tilde, we shall denote the space of real functions whose product with weight function, that is this product, on real numbers is bounded. Namely, we consider this set consisting of the function f from R to R, and the supremum of the product W tilde and absolute value of f of x is finite. And we denote by C0 the space of continuous functions on whole real numbers. We can also consider the following natural subspaces of BW. The first one, CW. CW is the intersection of BW and C0. And CW tilde star consisting of the functions f belonging to CW such that the limit exists. And CW tilde 0 consisting of the function f belonging to CW tilde and the limit equals to 0. And UW tilde consisting of the functions f, W tilde f is uniformly continuous. Okay, the linear space of functions BW, of course, its natural subspaces are norm space with this norm. Okay, we are considering this norm. And what about the weighted modulus of continuity? Here we will consider this weighted modulus of continuity for functions f belonging to CW tilde. And we will denote this new modulus of continuity with omega. Actually, it's not new because it's defined in 2001 by Nurhayat İsvir. And this modulus of continuity is given for positive delta as inequality 2. Here you see the weight function fx at denominator. And for details related to this general modulus of continuity, you can see the paper 33. And let us recall some useful properties of this modulus of continuity. The first one, the weight modulus of continuity is a monotonically increasing function of delta. And when modulus of continuity, weight modulus of continuity tends to 0 as delta goes to 0 for functions f belonging to CW tilde star. And for each positive lambda and f in CW, and the inequality holds. And in inequality theory, actually, in this inequality, if we replace the lambda with the absolute value of y minus x over delta, xy real numbers, and delta is positive, and consider the definition of weight modulus of continuity, we get this inequality. On the other hand, quantity of the absolute value y minus x with respect to delta direct us to do following inequality. Actually, we have two cases here. When the absolute value smaller than delta, we have this estimate. When the absolute value is greater than delta, we have this estimate. So by combining these two cases of absolute value y minus x, we get this inequality. And if we choose delta is smaller than 1, yes, since delta tends to 0, so without loss of generality, we can choose delta smaller than 1. In that case, we have this estimate. So this estimate, this inequality, will be very useful in order to determine the rate of convergence of corresponding family of operators. And let us see our first result proposition. Let Chi be a kernel satisfying the assumption Chi1, Chi2, and Chi3, but it will satisfy Chi3 for beta equals to 2. And future we denote by PC of x 1 over w tilde x. That means the quadratic 1 plus x square. X belongs to real numbers. In this case, the image of 1 plus x squared under the family of generalized sampling series can be estimated with the right side. So since we assume that the condition G3 is satisfied for beta equals to 2, that means the absolute moment of second order is finite. This means that M1 and M0 already finite. So this inequality is meaningful. And we can present an estimate for the operator norm that Chi be a kernel satisfying the assumption Chi1, Chi2, and Chi3 for again beta equals to 2. Then for a fixed W, the operator GW is a linear operator from BW to BW. And we have an estimate for the operator norm as in inequality 6. The first theorem, let f belongs to CW be fixed, then this convergence holds for every x in R. Moreover, if we assume that f belongs to UW, what was UW? UW is the f times weight function is uniformly continuous. So if we impose this addition condition, in this case, we have this norm convergence as well, of course, with respect to weight norm. And what about the rate of convergence in weight space of function? Again, let G be a kernel satisfying the assumption G1, G2, and G3. But now we are assuming beta equals to 3. Actually, we don't want to increase the value of beta because it requires a strong condition. But at least in order to give this result, we must assume this condition. In this case, for f in CW tilde, the norm converges of the generalized sampling series to the corresponding function with respect to weight norm can be estimated with the right side. So as a result of this inequality, what can we say? The norm convergence of generalized sampling series to the corresponding function f is at most 1W. Okay. And as a corollary, if we assume f in CW tilde star in the previous theorem, and by using the properties of weighted modulus of continuity, it was given in lemma 2, we have this norm convergence as well. So let us check the Voronozhskaya type theorem. Actually, Voronozhskaya type theorem was first given for Bernstein polynomials, and it states the rate of pointwise convergence of Bernstein polynomials to the corresponding function. But here we will present any form of Voronozhskaya theorem because in the Voronozhskaya type theorem, in the classical case, we are getting only the rate of convergence, but we don't have any information about the error of approximation. If you have an approximation process, it's natural to ask, what about the upper bound of your error? So in order to give the both information, rate of convergence and error of approximation, we will give the quantitative Voronozhskaya type theorem. In order to give such a theorem, we need to give an estimate for the remainder of Taylor formula. Remainder in the Taylor's formula at the point x in R is given by this equality. So we can write this right side in the form of 9. So here, Psi is a number lying between t and x. We don't know which one is greater, t or x. That's why lying between t and x. In the paper 3, that paper belongs to me with my PhD supervisor, Professor Ali Aral, and Professor Ion Rasha from Technical University of Cluj, Napoca. The remainder in the Taylor formula was estimated by using the weighted modulus of continuity as in inequality 10. So we have this inequality, and we have the power of absolute value t minus x with the power r plus 4. But when we obtain the similar result for generalized sampling series, we consider this estimate once again, because this estimation was obtained to present quantitative form of Voronozhskaya theorem for sequence of linear positive operators in weight space, and hence central moments of even orders. That's why here you see 4. Because in the approximation by linear positive operators, the positivity of the corresponding argument is very important. But here we don't have such a condition. because we have absolute moments, but in linear positive operators we don't have such a notation. So we can improve this inequality as in 11. So actually we are reducing the power at least one time. For jet is a natural number. The algebraic moment of order jet of a kernel G is defined by the following equality. So we have the following quantity Voronozhskaya type theorem. Let G be a kernel satisfying the assumption G1, G2, and G3 for beta equals to 4. If the derivative of f belongs to CW tilde star, then we have, I'm sorry, for x in R, that the inequality 12 holds. So what's the meaning of this inequality? Actually, this inequality tells us the rate of pointwise convergence of generalized sampling series to the approximated function f is 1 over w, because the right hand side goes to 0. If we suppose, in addition, the jth order algebraic moment equals to 0 for j from 1 to r minus 1, r is a natural number, and G3 is satisfied for beta equals to r plus 3, then we have for f r derivative of function f belongs to CW tilde star, the inequality is held. So when we compare these two inequality, actually here we have w, but here we have w with the power r. So we are increasing the rate of convergence from w to w to r, but the conditions are stronger and stronger. Okay, it's natural to ask whether there exists any example of the kernel G satisfying these all conditions. Yes, we will give some examples here. To evaluate the discrete moments of the kernel, we generally use the Poisson summation formula, and which implies that if the function u with the power g, chi u belongs to LOR. LOR denotes the space of Lebesgue summable functions on the real axis. Then the Fourier series of the jth order algebraic moment equals to the statement 14. And the Fourier transform of chi belonging to LR is defined with the following equality. And one of these examples is well-known B-spline. For a natural number n, the B-spline kernels of order n are given by the following equality. Here, the plus, r plus, denotes the positive part of the number r. And since Pn has compact support, the interval minus n over 2, n over 2, all the algebraic moments of jth order for the B-spline and the absolute moment, capital M of jet from jet 0, 1 to for all natural numbers are finite. As a particular case, let us choose n equals to 3. That means we are considering third order B-spline. So we have the explicit case of B-spline. The Fourier transform of B-spline will be like this. So now by means of Poisson summation formula, we arrive at the zero order algebraic moment equals to 1, 1, first order algebraic moment 0, and second order algebraic moment is 1 over 4. So this B-spline can be considered as an example of kernel satisfying the all conditions given results. So we can consider the linear combinations of translates of B-splines actually to obtain a kernel with higher order 0. Yes, let me turn back. Here we have a very strong condition, right? From 1 to r minus 1, we assume that the algebraic moment equals to 0. So the linear combinations of translated B-splines satisfy this condition. And we will consider the linear combinations and Tn with these combinations. The Fourier transform of Tn can be obtained like this. Again, using the Poisson's formula, it can be obtained for natural number n greater than equals to 4 that and zero order algebraic moment 1, first order algebraic moment, and second order equals to 0, and third order algebraic moment equals to minus 6 plus n over 2. So on the other hand, Tn is bounded and has compact support. So the interval 1 minus n over 2, 3 plus n over 2, which immediately yields that the third order absolute moment is finite. Okay, the first part of my presentation finished here, and I'm passing to second part. So in this part, I will talk about the generalized exponential sampling series. Actually, the generalized exponential sampling series was considered in 1980s as a solution of some light scattering, optical physics, and radio astronomy problems. And again, the first definition of this series was not given by mathematician. The definition was given by physics. So a similar significance of the theory is its connection to Mellon transform analysis, in particular, that can be considered as the Mellon analog of the classical Shannon sampling formula. And more recently, Carlo Bardaro from the University of Perugia constructed a family of linear positive operators as a generalization of the exponential sampling series and presented fundamental convergence properties of them. And what about the structure of generalized sampling series? The family of operators introduced by Carlo Bardaro are of the form of 15. Here, as you see, the sample is located exponentially. In classical sampling series, we are considering the equally spaced samples, but here we are considering exponentially spaced samples. Of course, this series is meaningful for function f, for which the series is absolutely convergent, and here phi is a function from R plus to R. We are considering the domain as R plus anymore, not R. Represents a suitable kernel function, and again, it will satisfy some certain assumption according to results and according to corresponding function space. And throughout the rest of my presentation, CR plus stands for the space of all continuous function defined on positive real axis, and CBR plus is the space of all bounded functions f in CR plus. A function f in CBR plus is called as logarithmic uniformly continuous on R plus. If for any positive epsilon, the definition of logarithmic uniform continuous is given, if for any positive epsilon there exists a positive delta such that ft minus f of x is smaller than epsilon whenever log t minus log x smaller than delta for any tx in R plus. So it's very similar to classical continuity, but we are considering this neighborhood. And by UCR plus, we denote the subspace of CBR plus consisting of all functions which are log uniformly continuous. Here, it's worth noticing that a log uniformly continuity of a function is not required uniformly continuity of the function in the usual sense, and conversely. So we cannot say if a function is continuous, we cannot say this function is logarithmic continuous or conversely. However, these two continuities are equivalent on compact intervals over R plus. And moreover, we will consider the space of CR, the space of R times continuously differentiable function. And the Mellon differential operator, or the Mellon derivative of f, the domain is again R plus, at the point x is defined with this equality, provided the usual derivative f prime exists, because the definition includes f prime here at the point x. Actually, the Malin analysis has many and very large information, but I'm just summarizing some required information here. Throughout the rest of paper, function 5 r plus 2r is called as a kernel. If the following assumptions are satisfied, it's again very similar to the to our earlier assumptions for classical sampling series. The first one is the series accused one for every u in R plus, and zero order absolute moment is finite. And in the second case, for every positive R, the limit holds uniformly with respect to u in R plus. And the class of functions satisfying these two conditions, I and 2i, will be denoted by phi. And the algebraic moment of order z is a natural number, is defined by the equality 16. And the absolute moments of arbitrary order alpha is defined by this equality. And let us also put m alpha phi. M alpha phi is independent by x just by taking the supremum of the absolute moment over x in R plus. And it's shown in 16 that the alpha order absolute moment is finite, then beta order absolute moment is finite for every beta between 0 and alpha. And for x in R plus, we consider the weight function 1 plus log square. And in the second part of my presentation, for exponential sampling series, we are considering this weighted function. And the logarithmic weighted space of function and its natural subspace are given like this. B2 B2 is the space of functions from R plus to R, such that this quantity is finite, and C2 is the set of intersections CR and B2, and C2 star is the set of the functions satisfying this limit condition, and LU2 is the space of F belonging to C2. This quantity is logarithmic uniform quantities. And the linear space B2 and its natural subspace is our norm linear space with the following norm. Actually, these spaces and the norm were defined by me, my student, PhD student, and Professor Ali Aral. And for F in C2 and positive parameter delta Aral et al. In 9 introduced the following weighted logarithmic modulus of continuity, because just later we will give the uniform convergence and pointwise convergence of exponential sampling series in weighted space of functions. And again, the next question, second question, will be what is the rate of convergence of this convergence? So we will determine this rate of convergence by using this weighted modulus of continuity, and this weighted modulus of continuity was first defined by us. And lemma, the weighted modulus of continuity has the following properties. The first one, if F belongs to C2, the quantity omega L is finite. If F belongs to C2 star, the limit of weighted modulus of continuity when delta goes to 0 equals to 0. For all F in C2 and for any positive lambda, we have this inequality. And for all F in C2 and HX positive, we can estimate the difference of FH and F of X with the right side. But unfortunately, here we must assume, we must take fifth power of this difference. It will affect the degree of absolute moment in the corresponding theorem. But we shouldn't find a better or lower, lower degree. And the result presented in this section were obtained in a collaboration with Professor Selcuk Acar and my PhD student Saadettin Kurşun, and recently published in Bulletin of Iranian Mathematical Society. And the first lemma, let phi belongs to capital phi. That means phi is a kernel with the condition the second order absolute moment is finite. Then for fixed W positive, the operators exponential sampling series is a linear operator. I'm sorry, direct with F here. It's a missing. Is a linear operator from C2 to B2, and it's bound. So it's well-defined. And the first theorem, let F in C2 be fixed and phi belongs to phi, and second order absolute moment is finite. In this case, this convergence holds for every x in R plus. In addition, if we assume F in LU2, that is F and product with weight function is logarithmic uniform continuous. In this case, we have the following norm convergence. And by using the new weighted logarithmic modulus of continuity, we can estimate the rate of convergence, or we can find an upper bound for the error of approximation or error of norm convergence, like right side. So we can say that the norm convergence of the operators to F at most 1 over W because of this inside term. So as a corollary of this theorem, if we take the limit of the right side, which goes to 0, which tends to 0, so we have the norm convergence from this theorem as well for function f in C2 star. And again, what about the rate of pointwise convergence? So we will present on the Wernicke type theorem. Let f be a function from R plus to C be a function in CR with a rich natural number R. Then for x in R plus and h in R plus, we have this formula. Actually, this formula is known as Mellin-Tyler formula. Yes, it's very similar to classical ones, except from this term. And here, the remainder is like right side. And from the Mellin-Tyler formula, we have the following inequality for delta smaller than or equals to 1. The remainder can be estimated with this right side. And the Wernicke quantitative Wernicke type theorem can be given with this inequality. Let phi be a kernel such that the sixth order absolute moment is finite. Suppose that the first algebraic moment is independent of x and it's different from 0. If the Mellin derivative of f belongs to C2 star, then we have for x in R plus that the following inequality holds. That means the convergence of pointwise convergence of exponential sampling series to corresponding f is 1 over W. And corollary, we have a corollary if we consider additional assumption like an generalized sampling series, that is the jth order algebraic moment is 0 from 1 to R. In this case, if the R Mellin derivative of f belongs to C2 star, then we have the following quantitative Wernicke type theorem. Yes, we increase it at the rate of convergence from W to W to R. And let us give some kernel examples of exponential sampling series. First of all, let us consider the space XC. Actually, the space is known as Mellin-Lebesgue space, and endowed with the norm, with this norm. And let f belongs to XC, then the Mellin transform of f is defined in the paper 20 like this equality. And the first one, Mellin spline kernels for natural number and the Mellin spline kernel of order n are given by this equality. And actually, we know that from the paper 20, B and tilde belongs to XC space. The Mellin transform of B and tilde equals to this term, and one can show that the series of the Mellin spline equals to 1 for every x in R plus. and using the Mellon-Poisson summation formula, which has the following form. So since Bn has also compact support on the interval e with the power minus a, e with the power a for positive a, all the algebraic and absolute moments of Bn are finite. As a particular case, again, let us consider the third order Mellon spline. It will be in this form. So using the Mellon-Poisson summation formula, we can calculate that first and second order algebraic moment of Mellon spline 0 and 1 over 4 respectively. And we can define the combinations of translated Mellon spline kernels. So the algebraic moment, 0 order, first order and second order, can be found 1, 0, and 17 over 3. And similar to Mellon spline kernel, combinations of Mellon translates are also with compact support kernel, hence absolute moments of any order are finite. So we have some examples satisfying the conditions of results presented in the second part. For other studies on sampling series in weighted spaces, you can see these papers. In this paper, we consider the weighted approximation for sampling Kantorovich series. In this paper, we consider the weighted approximation for sampling Drumeyer series. And in this paper, we consider a new form of exponential sampling Kantorovich series, and we examine the weighted approximation of the family of the operators. And in this paper, we consider the pointwise convergence of generalized Kantorovich exponential sampling series. And here we consider the bivariate generalized sampling series. Actually, consideration of bivariate sampling series is very important because at the beginning of my presentation, I told you sampling series is very important because of their application, because it has the application in image processing and signal analysis and the modeling of seismic waves and many engineering problems. So in order to compose an algorithm for these all application, we need the bivariate sampling series. So in this paper, we consider bivariate sampling Drumeyer series in white space of function, and here we consider bivariate generalized Kantorovich sampling series. And in a very recent paper, we consider a new version of classical generalized sampling series by modifying the operators, but our modification is very effective because we are getting a better rate of convergence and lower error of approximation. And here are my references. Actually, these references in this page were already presented in the previous page, so I'm passing these papers. But here I must mention the Bardaros paper, Bardaro with Butzer, Stens, and Winty. And this paper is very important when you consider discontinuous signals. And this paper considers the exponential sampling series, so it's related to Mellon analysis. This paper is a very recent paper, and it considers the bivariate generalized exponential sampling series in application to seismic waves. And it was published in Constructive Mathematical Analysis. It's my journal. So it's really a good paper. And here you have you see the papers of Bardaro, and this is a very main source for sampling series, a dialog approach to Mellon transform. Actually, when you consider the exponential sampling series, this is a main source. And this paper is again by Paul Butzer and again Paul Butzer. And here we have some recent papers as well. And this paper is very critical for and very important for the weighted approximation by Gatchiev, again from Gatchiev. published in Matsametki. And Ruhayat Ispir was the weighted modus of continuity was first introduced by in this paper by Ruhayat Ispir. And again, we have some recent papers. Thanks for your attention.
Thank you very much, Professor Acar, for the interesting talk. Thank you. And probably, may I ask you first, the usual sinc functions, they are a special case well, in the first part or in the second part of your talk, where the usual sinc function enters?
Actually, in the yes, you are right. In the original Whittaker Karapetyants Shannon sampling theorem, the corresponding family of operators includes sine C function. But my presentation is very long, so I didn't put the original one, and I started with the construction of Paul Butzer from Aachen. But you are right, the original Whittaker Karapetyants Shannon includes the sine C function. But sine C function has some problem in order to study the approximation properties. So that's why Paul Butzer consider any general function G here. So I didn't take a place in C function here.
Yeah, I understand. But is it a special case in your scheme or not? This is the question.
No. It's no. Not, because this Q function is defined to get rid of the difficulties of sine C function. So this Q function is not including the sine C function.
Okay, thank you. And another question, there is no Paley-Wiener theory behind your results, yeah? You don't need
Yes, no Paley-Wiener theorem in this presentation.
Okay, and so more or less how you prove the uniform convergence?
Uniform convergence,
yes.
Yeah, we are just considering the conditions of, let me show, just a moment. Yeah. Actually, we are considering the pointwise convergence in this theorem just by taking the supremum over X. We are just finding the norm convergence because we are assuming an additional condition if F in UWT. So this condition is enough. So we don't need the Paley-Wiener theorem over there.
Okay, thank you very much.
You're welcome.
So please, questions.
May I have one question?
Yeah, please.
Yes, please.
Well, about your modulus of continuity that involves log function.
So you are talking about the
modulus
logarithmic.
Of continuity. Yes.
Which one? Logarithmic weighted modulus of or classical weighted modulus of continuity?
Logarithmic.
Let me show. Just a moment. Let me show this one.
Yes. So what's the reason of choosing log function? Because you can choose any similar function that vanishes at 1.
Yes, you are right. It's a very good question, because here, let me show. Here our moments includes the logarithmic function. So in order to make our calculations easier, we are just choosing 1 over logarithmic square. Or as I said in the first part of my presentation, you can select any other weight function. But
yes,
in order to make our calculations easier, we are choosing this function.
Yeah, it makes sense. Right. Okay. Yeah. Well, one more question just for understanding. You divide by log of x and log of t just to avoid the behavior at the infinity, right?
Yes, yes, yes.
But if we speak about the local modulus of continuity, if we are staying at stay interval, we don't need this division, right? The
Yes,
denominator.
you're right. Yeah, yeah.
And then, for instance, if we stay inside of interval and you don't use this denominator, you just have ftx minus ft, etc. And what's the difference between this log modulus of continuity and classical? Can you compare them?
Actually, yeah. Actually, in the numerator, we don't have f t minus f of x. We have f t times x minus
Yes,
f of
yes.
x. So this will solve our problem, right?
Well, I see it's kind of different. Yeah, I see.
Yes.
Yeah, okay.
Thank you. More questions, please. So I think there are no questions. Yeah. In fact, I think your results can be very useful in inverse coefficient problems, for example, for Sturm-Liouville equations. So
Yes. Yes.
probably we can, well, write to each other by email.
Yes. Okay. Okay. Definitely. I'm welcome
Maybe
to all open and closed problem.
maybe I ask one more small question, if you allow me.
Yes.
What about complex analysis? If you inside of complex domain, trivial domain unit disk, did you do
Actually, I
any?
have never studied the approximation on complex domain because, yes, I have never told about the applications of a sampling series, but we are studying the image processing application intensively, but uh, it's it's it's uh, it's done under a project of TÜBİTAK, the Scientific and Technological Research
Yes,
Council of Turkey, and we have an algorithm over there. So I cannot present that algorithm right now because there is some restriction.
I see. I see.
So I am directing myself to real world application problems. That's why I'm considering the real cases. That's why I considered the many bivariate cases of sampling series. But yes, the complex case is an open problem. And by the way, I have never seen the complex cases yet.
Yeah, I understand, but you know your idea when you just constructed modulus of continuity by inserting radius, say, inside of argument. This idea also works in complex analysis because using the properties of holomorphic functions, you can describe alternatively the holomorphic functions in such terms, but you still need some smoothness conditions on the boundary. But well, it's a big different question. Okay.
Yes, yes, very big difference question. Well, thank you.
Okay. So probably I'll ask you for some papers of your just to see to have a
Okay,
close
okay.
look.
Of course, of course.
Okay, perfect.
Thank you.
Thank you.
By the way, as I said in my references part, this journal, Constructive Mathematical Analysis, is my journal. I founded the journal 6 years ago. It's an open access free journal, and now the journal is indexed by Web of Science, Emerging Sources Citation Index, and its quartile is Q1, and the impact
Perfect.
factor is 1.1. And we are very selective for this journal, and we are publishing 4 issues, and in each issues we are publishing 5 papers. But till now, I have never uh, received a submission from Russia. I'm sending many invitation emails to colleagues, but I cannot get any submission. So I am inviting you to submit your papers to constructive mathematical analysis. And as an application of our journal, we are organizing the conference series. Actually, this conference, this flyer, is for the third edition of the conference. In 2019, we organized the first one. In 2023, we organized the second one. And next year, on July, we will organize the third series of the conference. So I am inviting you all to participate at the conference. Okay, I just wanted to inform you.
Yes. Okay. Perfect. Thank you. I know about this
You're welcome.
conference. Yes. I hope we will be able to come.
Thank you. Thank you so much.
Thank you for this information. Where is it? Where is this conference?
In Konya, at Selcuk University,
Konya.
at my institution.
Okay. Perfect. Thank you. Okay. More questions or comments?
It was very clear presentation, good discussions.
Thank you very much.
Thank you so much.
Really interesting. Yeah, thank you.
Thank you. Thank you so much.
Thank you.